Right, now with the fragmentation that we have available to us with ketones, we can use this to solve interesting problems. Remember that with ketones we have available to us alpha cleavage and we have McLafferty rearrangement mechanisms available to us to explore what fragmentations can happen with ketones. So here's an interesting problem. As usual, some samples have become mixed, and so we have two spectra of 3-methyl-2-pentanone and 4-methyl-2-pentanone. And so what we need to do is we need to try and explain, try and match one of these spectra to one of those compounds and the other spectra to the other compound. And so that's interesting. You'll notice that we have M over Z of 43. It's a base peak in both cases. And of course you can see the molecular ion of 100 in both cases. These are isomers of each other. They're going to have the same molecular ion. So that's not going to help us. And the base peak, because these are ketones, I can see that it's a methyl ketone because M over Z 43 would come from alpha cleavage of the ketone. So let's just have a look and just check with both compounds. So here we have, here's the 3-methyl-2-pentanone, and let's have a look at what alpha cleavage looks like. Remember that when we provide a high energy electron, we knock off an electron from the compound, and it's going to be a lone pair electron. And so I'm going to knock off that electron at the top there to leave a positive charge. And then I can use half arrows to show the fragmentation, and you can see we get M over Z 43 really nicely in this from 3-methyl-2-pentanone. Do we get the same thing from 4-methyl-2-pentanone? Yes, here's 4-methyl-2-pentanone. Here's the 4-methyl, the methyl group's now here, but of course when you fragment it, you get that M over Z of 43, and of course you get a radical which has no charge, and so will not appear on the mass spectrum. Okay, so of course alpha cleavage gives rise to M over Z of 43, but is present in both spectra. So alpha cleavage is not going to help you identify which compound is which. What would be interesting to see is the McLafferty rearrangement, because both compounds have got alpha, beta, gamma hydrogens available to them, and so the McLafferty rearrangement is available in both cases. So let's start with 3-methyl-2-pentanone, and I've drawn the compound out so that a gamma hydrogen, there are 3 gamma hydrogens, but one of them is in close proximity to the oxygen. Then of course when we knock off a lone pair electron, we can then pair the electrons with this bond over here, and of course the radical moves to this end and the charge fragment, and of course the pairing of electrons gives rise to a very stable alkene, and that alkene has no charge, so it will not appear in the mass spectrum. But of course it's this bond that breaks. One of these electrons pairs with this unpaired electron over here to form the double bond. The other electron goes to this alpha carbon over here. And of course if you calculate for this, it's got a charge of 1, so it will appear on the mass spectrum, but of course we've got 1, 2, 3, 4 carbons, 1 oxygen, and 3, 4, 5, 8 hydrogens. We find that when you add those all up together, it's M over Z of 72. So when you go back to your spectra, have a look at your spectra. Is there an M over Z of 72? Yes, M over Z of 72 appears here, so this must be the 3-methyl-2-pentanone. But can we confirm it with another mechanism? So yes, M over Z 72, only one spectrum has that, and so that must be for 3-methyl-2-pentanone. Let's have a look and see if we can't do McLafferty with the other compound. And so this is 4-methyl-2-pentanone. I've drawn it, and in this case there are 6 gamma hydrogens. These 3 are all gamma hydrogens, those 3 are all gamma hydrogens, but I've drawn one of those gamma hydrogens close to the oxygen. After knocking off electron, we have a positive charge. We can break that bond. One of those electrons pairs with this electron to form a bond on this side. The remaining electron goes to the gamma carbon, and then of course we can pair that electron on the gamma carbon with one of these beta electrons. This bond, we cleave that bond, and one will go to the alpha carbon and one will go to form a very stable alkene, which has no charge, so will not appear on the mass spectrum, but its stability will drive this whole process, this rearrangement, because we're forming a highly stable product over there. Of course, the charge fragment with a plus, the charge fragment that does appear on the mass spectrum, has 3 carbons, 1 oxygen, and 6 hydrogens, and we add up with carbon mass 12, oxygen mass 16, hydrogen mass 1, you get a charge to mass ratio. The mass is 58 and the charge is 1, and 58 over 1 means that it will appear at m over z 58, and so you can see that there it is on the mass spectrum. So the peak at 72 was McLafferty of 3-methyl 2-pentanone. The peak at 58 is McLafferty of 4-methyl 2-pentanone. So quite easily we can distinguish which is which from looking at the McLafferty arrangement. I haven't done everything that I could possibly do on these two spectra. Of course, with 3-methyl 2-pentanone and 4-methyl 2-pentanone, there's another alpha cleavage that could be performed. So it'll be interesting if you would be able to do another mechanism, a different alpha cleavage for both of those compounds, and see if that provides any additional evidence as to which spectra belongs to which compound. But the McLafferty at least has told us which is the case.